Hello, I welcome you all to the lecture session on Introduction to Digital Electronics. This session will brief about general concepts on two types of digital circuits, combinational circuits and sequential circuits, and examples falling under each category. Digital circuits can be classified into two types, combinational digital circuits and sequential digital circuits. In combinational digital circuits, combinational logic circuits are made up of basic gates such as AND or NOT, or universal gates NAND and NOR gates that are combined or connected together to produce more complicated switching circuits. These logic gates are the building blocks of combinational logic circuits. An example of a combinational circuit is a decoder, which converts the binary code data present at its input into a number of different output lines, one at a time, producing an equivalent decimal code at its output. In these circuits, the outputs at any instant of time depends on the inputs present at that instant only. For the design of combinational digital circuits, basic gates such as AND or NOT or universal gates NAND and NOR are used. The block diagram of combinational digital circuit is shown here. Examples for combinational digital circuits are half adder, full adder, half subtractor, full subtractor, code converter, decoder, multiplexers, demultiplexers, encoder, ROM, etc. The three types of combinational circuits are arithmetic and logical functions, data transmission, and code converters. These three classifications are required for a general transmission and reception communication system based on digital systems. In sequential digital circuit, the sequential logic differs from combinational logic in that the output of the logic device is dependent not only on the present inputs to the device, but also on the past inputs. That is, the output of a sequential logic device depends on its present internal state and the present inputs. This implies that a sequential logic device has some kind of memory, that is its previous states. A simple memory device can be constructed from combinational devices with which we are already familiar. By a memory device, we mean a device which can remember if a signal of a logic level 0 or 1 has been connected to one of its inputs and can make this fact available at an output. A very simple but still useful memory device can be constructed from a simple OR gate as shown here. In this memory device, if A and Q are initially at logic 0, then Q remains at logic 0. However, if the single input A ever becomes a logic 1, then the output Q will be logic 1 ever after, regardless of any further changes in the input at A. In this simple memory, the output is a function of the state of the memory element only. After the memory is written, then it cannot be changed back. However, it can be read. Such a device could be used as a simple read-only memory, which could be programmed only once. Often a state table or timing diagram is used to describe the behavior of a sequential device. This figure shows both a state table and a timing diagram for this simple memory. The state table shows the state which the device enters for all possible states and inputs. For this device, the output is a value stored in the memory. Note that the output of the memory is used as one of the inputs. This is called feedback and is characteristic of programmable memory devices. Without feedback, a permanent electronic memory device would not be possible. The use of feedback in a device can introduce problems which are not found in strictly combinational circuits. In particular, it is possible to inadvertently construct devices for which the output is not determined by the inputs and for which it is not possible to predict the output. A simple example is an inverter which its input connected to its output. Such a device is logically inconsistent. In a physical implementation, the device would probably either oscillate from 1 to 0 to 1 or remain at an intermediate value between logic 0 and logic 1, producing an invalid and erroneous output. Examples for sequential digital circuits are registers, shift registers, counters, etc. I would like to conclude this session with the general idea of classification of digital electronics based circuits with two types, combinational and sequential circuits. Combinational circuits are the one concerned about the present state of the inputs, whereas the sequential circuits also taken the condition of the previous states using some memory storing elements. I have also touched upon the examples of combinational and sequential circuits, where we can investigate a detailed analysis of those circuits to build an efficient digital system. Thank you.